Hey folks, nice to meet you. And I'm going to present my project that actually has a quite long history, and I'm going to tell a bit more about how kind of I moved to this point. I started work like maybe a month or two ago, and then wanted to present it and to share my thoughts and kind of see the reaction of great engineers, because frankly, I see this idea really great, but you know, it's my idea, so it's a kind of, it's a bias in some way. So yeah, it's nice to have an opportunity to share my thoughts with other engineers and hear feedback. Okay, so about me, my name is Anton. I work as software engineer in Berlin at Klockner.ai company. It's a kind of child company of big Germany concern or even holding of several companies that sell steel and other metals. Yeah, and we have a great team of Elixir engineers and still looking for even more great engineers. So if you're interested, please reach out to me or to the to Alice. You see her on the slide. Yeah, I want to say thanks to Sydney Meetup, because when I decided to share my thoughts, to share this framework, first I reached out to Berlin Elixir Meetup, but it appeared that it's not so frequent, like once per 2 or 3 months. Then I started Google other meetups, and it's kind of empty space, and the only active meetups are in Sydney, and also found Denver that are still active. So yeah, please guys, do more of such meetups. We as engineers have to discuss things, share thoughts. Otherwise we will just follow like authoritative opinion of big companies and consultancy agencies. I kind of wanna see like true engineering way from the bottom. So we discuss all the interesting things and decide in community what is cool and what is not. So yeah, let's go. So presentation is like, and framework, and the presentation is more about application layer of the program. Okay. Just quick recap, what is application layer? Yeah, following our classic Eric Evans and domain-driven design, the common like division of the application into four layers: infrastructure, domain, application, interface layer. And kind of we as a backend engineer mostly work on these 2 layers: domain layer and application layer. In domain layer, we kind of abstract external world with our programming abstractions, yeah, and build kind of domain language. And on application layer, we just use this language to express what our program actually does. Yeah, and we can put it, if put it very simply, I would say that the domain layer is about creating the language, and application layer is about telling the stories, the story of your program using this language that is created on domain layer. And basically, because we write these layers using the same programming language, frequently it happens that there is no clear division in our program between these 2 layers. Everything is a bit messy. One function called another, then like trio function, etc. And it's kind of hard to understand where is actually application layer and where is domain layer. It's always kind of keep together. So yeah, so the idea of the framework is actually to split these layers, to give another way of thinking, another language for presenting application layer, and kind of divide or split like on a kind of thinking level this domain and application level. So they kind of use different language for that. Let's say like interface layer. Remember that a long time ago we used like Rails framework, and we program all the logic, domain logic, logic in controllers, and also we programmed views. Then when application became more complex. We kind of delegate this interface layer to front-end guys that speak different language like JavaScript. So we kind of we're constantly trying to like divide responsibility to keep things simple and like more clear. Okay, so the first part is kind of my journey to flow-based programming. Actually, the story is started quite long time ago, maybe 10 years, I would say. At that time, I worked with guys on insurance agency company, and we kind of automate this insurance agency flow, and we used Ruby on Rails at that time. And you know, like in Ruby on Rails, when you start, everything is okay, but if your application become a bit more complex, it's always create a mess. And at one point, one of my colleagues found a great library, gem, called Interactor. The idea of the gem is very, very simple. You can define interactors. It's just a class with one method call, like find user. And kind of put logic that is responsible to this operation or to this command, let's say, into call method. And the great idea is that you can combine these interactors into chains, like organize them into chain. And there is a class method organize, when you can put like several interactors, find user, find products, create order, check out users, and send email, and kind of define your application layer, I would say, in a very straightforward declarative manner, like a consequence transformation of some data, one after like step by step. So and we really like this idea actually, because we use these organizers on a high level, like on a almost interface layer. So in controller, place order organizer is called, and then all these interactors that inside it organizer are sequentially called. And this idea was really great because it was simple. So basically, all these interactors under the hood works with the same data structure. Let's say they share one context object. Yeah, it's Ruby, object-oriented language. So they share one common context, and each interactor just modify this context. Find user, like put user to this context, and find products, finds products for this user and put into the context, and create order interactor, combine all these data and creates order, etc., etc. Okay, so and why it was cool? Because why it's like simple and clear. Because actually with this interactors, with this organizers approach, you kind of tell your story as you see it in a feature requirement. Yeah, like in order to place order, you first need to find the user, and in your kind of engineering mind head appears a find user component. Then products should be selected. Okay, there will be a products component, etc., etc., etc. So it's kind of very a natural way to translate feature requirements into this high-level business logic that we put into our application layer. And yeah, and basically the similar approach we have actually in functional programming. Yeah, it's like a sequential processing of data structure. Yeah, and in Elixir we have this chain of functions or with statement, when we just like put the data, and this data transformed consequently in each function. And we like functional programming, I think, first because of this approach, because we don't need to keep in mind that this object has other object inside that will process something. No, we just have functions and data that are consequently transformed by this function. And it's really simple and expressive way to to introduce to write our application layer. I can't open chat for some reason, but I see that there is a message there. So if there is a question, please just stop me and ask this question. Okay, then and again about this approach of chaining like components. You know, from Elixir community there is a plug library that is also designed in the way that you define simple like logic, simple components that implement only one function call, and then you can combine this function plug one, plug two, plug three, etc. And all these plugs kind of works on one data structure, the big data structure con, when you see like parameters, headers, every information you can put there. And actually the same approach was used in Ruby rec library. The abstraction they called middleware, and again it has just one method call, and you can stack these middlewares one by another, and each middleware just called with this environment variable where all the data needed for processing output. Okay, so it was beginning. It was kind of Ruby, and in Elixir, where kind of the idea actually born. It was like 5 years ago. Jose Valim did a presentation about GenStage library, and yeah, let me quickly tell about what the library is, because I suspect that maybe some newcomers didn't see it before. So basically, the idea of GenStage library is to put organize like GenStage library. GenStages is an abstraction on top of Gen servers that we know in Elixir. But GenStage library allows to connect these Gen servers in a proper way, like subscribe to one to another, and kind of GenStage library handle all these infrastructure communication layers. So you as engineer don't need to kind of decide to which process you want to send message. You kind of define this topology at the very beginning, and you kind of know, you subscribe these consumers and producers, and you know in advance where this event go, and the only things left is to implement this handle events callback in each component. When you kind of receive events, do something, and send events further to the next to the next component, to the next gen stage. Yeah, and actually, when Jose Valim presented this library, he started from like simple examples like numbers, goes from producers, like calculates like sums, multiply something on something, etc. But after that, he showed an example where in one of the components he did call to a database, and this kind of triggered me that Jose Valim kind of put a business logic inside these producers and consumers, and it's really triggered with this interactors and organizers approach, because it was like really similar. We have like several components, several processes that chain into one pipeline and then can process data. So it's really the same that we had in Ruby. The same, I mean, in the way how you like think about program, not the details of implementation. So yeah, that is how idea born. And actually, when I started Google this approach, like to put your own code into independent processes, I realized that this idea is really old idea. It's from early 70s. The author is John Paul Morrison. There is also a book about that. I cannot really recommend the book. There are lots of technical details, and the components that are described there are quite low-level ones. So I think for you, it's just enough to to check the ID, or just Google this flow-based programming and you got everything, and you get everything that you need. But yeah, if you need more details, you're welcome to read the book. So basically, what is flow-based programming? It's a way to define your application as a transformation of data, as transformation of data that flows through components. There are components like independent processes, independent black box processes that just connected in some way to each other. So you kind of have this topology in advance, you know what is connected to what, and each black box just process messages and like send messages to other components. And by messages, I mean like in a broad sense, like business event, like something happens, request or whatever, and you abstract it as a message with all the data. In flow-based programming, there is an abstraction, this abstraction called information packet, or IP. So you kind of abstract this event into this information packet, and then this information packet goes through several transformations, and finally you get the final information packet that is the kind of result of your program or specific flow in your program. Okay, so what are the benefits? That's what I mentioned at the very beginning. That in this way, flow-based programming suggests like a different language, way of thinking for the application layer. So you kind of define your domain layer, all these components that are responsible for creating user, billing user, sending emails, etc. And on a higher level, on a top level, you just define the flow of your program, and in a different language, in sense that your domain, your components may be implemented or is implemented, if you talk about Elixir, in Elixir programming language with a kind of conventional flow-based programming. But on a higher level, you have flow-based programming, so just message passed, yeah. And also this component actually can be language agnostic. You can implement component in different languages. Yeah, it's like your domain. You can use everything there, but on application layer, you just have like components that connected in some way. Yeah, and this brings this like clear separation of concern, I would say, or clear modularization, that every component is responsible for some business logic, and they are completely decoupled in some way. Yeah, so they decouple it in the way that they don't know any functional details about each other. They are coupled only by data that passes through these components. Yeah, and the great feature is so-called design and runtime observability. So basically, when you design your program, you kind of put these components on paper, I don't know, or draw diagrams. And when you run your program, you actually have the same. You have the same components, independent processes that handle these messages. And intrinsic parallelism, in flow-based programming, these components are kind of absolutely independent processes. So in a true implementation for flow-based programming, each component is a kind of separate process that works absolutely independently from other processes. So you can put many events or many messages into your pipeline or graph in flow-based programming, and while one component works on one IP packet or message, another component can handle like previous one or the next one, so they kind of can do work in parallel. Okay, and it's extremely easy to implement flow-based. Yeah, first of all, I would say that there are lots of implementation actually of flow-based programming in different programming language. You can Google it. At least I know about quite popular NoFlow.js library, JavaScript implementation of flow-based programming. But there are implementation in different languages. But in Elixir and Erlang, the implementation of such an approach is extremely easy, not difficult, but easy, because we have at the very beginning, we have this actor model in Erlang, where you kind of the main abstraction is a process that exchange messages. And also in Erlang, we have a very powerful Gen server abstraction that allow us to start these processes, stop, monitor them. Yeah, so all this logic, and also easy to implement all this handle, class handle, callback. And finally, GenStage, a library that allows like easily predefine this topology, this kind of the way that components are connected in your code, like in advance. So you don't need to worry about where to send this message. And also the great feature of GenStage that it also provides a so-called back pressure mechanism. For example, if you try to implement flow-based programming using just plain Gen server, you might have a problem when one component is a bit slow and the previous component sends messages to this slow component, and this component like become overflow by data. Yeah, but in GenStage, the asking for data is kind of reversed. So this slow component asks new payload only when it's free. So this problem of overflowing data is also solved with GenStage. So yeah, that is how FlowX, my first attempt to realize to implement flow-based programming appeared. It was quite a long time ago, and I decided to start just from simple linear pipes of these processes, because again, as I mentioned, the idea, like the roots of idea is are in this organizers gem from Ruby. So for me, I just decided that it might be enough to build like just a simple straight chain of processes for this implementation. And I call this approach a railway flow-based programming. So there is no branching. Your packet can go just straightforward from one component to another. And the implementation is quite simple. So basically, there are gen stages like add 1, multiply 2, minus 3. It's a really simple example just to illustrate how it works. So and during the compilation, during the start time, when you define this pipeline, these processes are started and producer consumers attached. All these processes are under supervisors, and you kind of put your code into these components like add 1, multiply 2, etc. And yeah, and on this slide, you can actually see how it looks like in your code. So there is a quite simple DSL when you combine these components using pipe macro, and then goes the function name, and this function will be called during runtime. So this function kind of is put into GenStage and called inside this GenStage. And actually, we use FlowX in production in the company I mentioned, insurance agency. We used it for, I call it homegrown ETL pipeline. At the time, in the very beginning, there was no money for like big solution of that. So we decided to implement something simple on our side. And the idea of the project was just to connect to different databases in our not micro, like service-oriented architecture, and just collect all the necessary data from different database, transform them in some way, and then put like clean data into one database that is used by data analytics of our company. And really, it's worked like a charm. So I kind of was even surprised how robust and how robust GenStage library, or even like the whole Erlang ecosystem is. What was bad is basically that this project was only about data. So basically each component just transformed data in some way. Yeah, but my original idea was a bit on a higher level, that it's not just bytes or some meaningless data, but meaningful business events. And actually in 2019, the Broadway library appeared. Yeah, so no need to use Flowux for processing data, absolutely, because Broadway is kind of designed for processing big amount of data. And also because of Flowux implemented only these straight chains of processes, it wasn't enough to express the whole logic of transformation. And sometimes you have to put some conventional, not FB, sorry, if mistake, conventional functional programming logic, I would say, alongside with flow-based programming logic. So you always like have if, and if something, you have to put data into another pipeline. So it's looks like a bit messy, because you kind of mixed two paradigms in your code. So yeah, but there are lots of changes since Flowux appeared. Currently, GenStage library is more than 1.0 version, so it's quite robust. Dynamic supervisors appeared in Elixir, because in Flowux implementation there were no dynamic supervisor, and there is a quite messy code that combines, that builds all these, build this pipeline, subscribes processes to one another. So it's like too much metaprogramming, I would say. But with dynamic supervisor, it's much easier to start processes during runtime, dynamically start processes and subscribe to another process. So it's much easier now. The next big feature that appeared in Elixir is streams, that you can actually use a very powerful abstraction to control how to feed actually the pipeline. So and kind of to chain different streams from different sources. Yes, a very powerful abstraction. And also a telemetry project that I think that everyone in Elixir community likes a lot, like a simple set, like simple interface to collect telemetry and to attach additional logic that will use this telemetry and show beautiful graphs and diagrams. So yeah, that is how we decided that it's time to improve Flowux a bit, but improve Flowux kind of was written a long time ago, so improvement was almost impossible. So basically ALF is written from scratch, and the idea basically is the same. Again, you just put your code into GenStages. There is a pipeline supervisor, dynamic supervisor, that kind of collect all these collect components and put everything in places. And there is also like pipeline manager, basically a separate Gen server, just starts, stops pipeline and feed data to this pipeline and gets the result from the pipeline. And first interface was changed a lot. So the main interface currently in ALF is stream interface. I suspect there are so many questions, but guys, I can't open the chat. I will answer all your questions a bit later. So, or just interrupt me if you got lost. So yeah, basic interface is stream interface now. So when you start pipeline, you just get enumerable or stream in Elixir abstractions, and stream these enumerable to the pipeline, and you as a kind of, and this function stream2 basically returns also stream. So you can join several streams or just put enum to list to run this stream and to get the result. Also, you can stream many streams into one pipeline. The example below, when there are 3 streams that stream into one pipeline, and then you just await while all the streams are ready. Also, there is a client abstraction currently that allows you to synchronously kind of got results from your pipeline. Basically, each client is a separate Gen server that runs like infinite stream inside. And when you call this client, the client put your data, your event into the stream and stream to pipeline, and then wait until it's done and return the result back. And there's also idea to create a client pool when you kind of when you don't need to create a client each time, when you but you have like a pool of clients that are started in advance during runtime, and you just send data to the pool, and on the pool level it decides which client to choose, which pipeline to choose, etc. But it's on a very early stage of development currently. Okay, and let's check components, because ALF is much more powerful than Flavok. There is not only straightforward pipelines. There are lots of different other components. One second. So basically, let's quickly go through these components. So basic component, it's stage. It's kind of the main components where you put your logic. And the logic that will be executed in the component may be put either into two-arity function, like my fun on the left, or if the logic is quite complicated, you can extract it to a separate module, and this module should implement call function that will be called inside this stage. And also optional init callback that evaluated during start time of the pipeline. And also producer consumers, just the simple GenStage producer consumers that feeds data and then receives data. There is a switch, very important component, because as I mentioned before, it's really hard actually to present the whole application logic without branching. Sometimes you definitely need branching. If something, if A equals 1, you have to do this. If A equals 2, you have to do that. So it's much easier to implement when you have like switch statement, when you can direct your component into specific pipeline. There is also clone component. The idea of the clone component is to perform like aspects of your program or background processing when you have like main flow, and also you have to do like some additional background task. This component will just clone a packet, and this clone will go to another branch of your pipeline. There is also goto and goto point components. Yeah, goto is quite controversial, and we know that goto is a really bad idea in programming. But I would say that in flow-based approach, the goto might be okay, because we know that goto is bad from old school programming language like C or BASIC. When you go to somewhere, you go to completely different universe, completely different function or procedures, completely different data, and it's absolutely impossible to kind of track in mind where kind of going. That is why goto is really bad. But in flow-based programming, goto means that you just send packets to some component. So you kind of switch a context of like functional context, but you're still in the context of the same data packet or the same event. So in that sense, goto doesn't seem really complicated. And also in ALF, I decided to implement explicitly the goto point component. So you kind of see in advance where your packets may go. Yes, and this much clear. And even kind of more philosophical point for this goto, in original flow-based idea, the flow-based programming idea, this you kind of build a graph of your components. These components can be connected in a different way. So in a mathematical sense, you have like a graph. With GenStage, in GenStage library, you can just subscribe GenStages and build a tree, not a graph. So you always kind of have one flow. So that means that in order to to implement a real graph or logic that can be described only in graph, you actually need this goto to make like these additional links that are present in graph, but impossible to present in a tree structure. Okay, and getEnd just a kind of component that like do nothing and your packet disappears there. It's really useful again for these background actions when you have to implement some background actions and don't need any result. You just put getEnd and that's it. Plug and plug two specific components that is used when you want to combine different pipelines. Currently in ALF there is a macro stages from, so you can define several pipelines. And then like your main pipeline, and then when you define your top level pipeline, you can just put these pipelines, stages from these pipelines into your main pipeline. And these stages are wrapped by plug and unplug components that just transforms data, just prepare data like adapters for your internal pipelines. And also two very powerful components, decomposer and recomposer. Extremely powerful, and one should be really careful with them because decomposer and recomposer can create new events. Decomposer actually allows you to create several events based on one event. So for example, if your business logic needs to do some different stuff as a reaction on some data, in Decomposer, you just consume event and creates like 2 or 3 or several other events. And Decomposer does the opposite. Decomposer kind of collects events and can like create one event from many events. Yeah, it's really powerful, but I will not spend lots of time on that. Okay, and you can see how it looks like on a very simple example, bubble sort of a list. So here you can see producer, then first component just build a struct needed for operation of this pipeline. Basically, this struct has an initial list that you want to sort and some additional information like what is the maximum element in this list, the new list, the kind of sorted list that you will return. So all this data struct is prepared and built struct components. Then data goes to find max component. Find max component just find max element in the list. Then the next component updates this new list. The next component rebuilds the previous list. Then just for an example, I put the clone element that kind of report step, write some logs that, okay, first iteration is done. And then go to if component, it just checks if everything is sorted. If no, it goes to go to point and do the same again. And when the list is sorted completely, output is formatted and the result is ready. Okay, and how this pipeline
I have a question, Anton.
Yeah, please.
So just to make sure that I understand, so a go-to point is saying that this is a designated point that a go-to can go to, and the language gets a little hairy there, but it's saying it's kind of a predefined point which you can come back to later. Is that correct?
Yeah, it's also gen server. Under the hood is also gen server that is just can handle packets from this go to if component. And if you take a look on this DSL example, you can see that go to, you see the second from the bottom, go to, you kind of specify where to go. And you just specify go to if, it's kind of function. It will check if you have to go or not. It's kind of Boolean functions that should return whether you go to or not, and then you specify to go to point. So you kind of explicitly specify where the packet will go if condition is true.
Thank you.
Yeah, so let's see how it looks in ALF DSL currently. So all these components that you see on diagram, you actually see during coding time. So you kind of declare this tree of components using very simple DSL, define your stages, go to points, etc., and automatically it builds this complicated tree structure. Yeah, that's about DSL. And take a look here on this count statement. Basically, it was introduced even in Flowx. The idea is that sometimes some of your component may be quite a slow ones. Yeah, imagine that one of your component does API request to some third-party API, and you have to wait like 10 seconds until this API responds. So if there is only one component that do this logic, then other components will just wait until this component finish this call. And the idea with count is that you can create like copies, clones of one components. All these components will be subscribed to the same previous one component. So when packets go through the pipeline, they will kind of distribute it between these 10 components, and they will work in parallel. So you can like make 10 parallel requests to API, and your pipeline will work much faster. And this idea is also implemented in ALF, and I call this feature like controlled parallelism. When you specify this count during development time, you can declare how many components you wanna to work on this particular logic. Okay, and then even more buzzwords here, or buzz phrase: design, coding, and runtime observability. So basically, you saw this DSL. That means that when you design your application, you put these components, build this tree. When you code your application, your pipeline, you also kind of see this tree inside the components section when you use this DSL. So you also kind of see the tree that you draw during design time. And of course, in runtime, you also have the same picture. You also have the same component that interacts with each other. And on this slide, I put an example. Currently, I work on a small tic-tac-toe online game, and I want to kind of implement the backend of this game using flow-based programming approach, using ALF. And you can see like one pipeline that is responsible for like initial event when user enters the game. Yeah, and user enters the game, and you can kind of read what will happen in the program. First, we validate input, then we check if a token present from the client in this event. If token present, it means that there is a client that already registered in the game. If not, it means that it's a new client. So you see that if there is no client, we first find users with the game. With the name, sorry, yeah. The logic that if the name is taken, I just add a postfix to the name and create user. Yeah, then after user is created, we find free game. We try to find free game. If there is a free game, we assign user to game, etc., etc., etc. If token is not present, so we go to this top floor. We first find user by token, then find active game. Then if not, we find if not active game, we find waiting game. And if we found game, you see this go to statement, we go directly to prepare the game. If not, we do the same steps, find free game, if not game, blah, 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 blah. So yeah, you see how it's really like clear and expressive way to present your logic. And upcoming killer feature that is I'm looking for collaborators to help me a bit with that. So basically, the first feature is detailed monitoring. Currently, telemetry is implemented in ALF, but on a very basic level. But the idea is really, really huge, because actually with this flow-based programming approach, you can monitor every stage on your application layer. So you can actually react on events when packet enters component. You can see when packets go out from component. So you actually can have a statistic about each phase in your program. And of course, it's based on telemetry libraries that we have in Elixir. And another super cool feature is in browser visualization, or just visualization of this pipeline, because again, it's just a tree of components. This tree exists in the code. You can send this tree to JavaScript library or use Phoenix Live View and just to basically build all these components and show them in browser. And even during runtime, you can fetch information about all these components and even show like how many packets this component has processed, or even maybe like show me like 10 last data packets that was processed in these components, and to check in runtime what is going on. So yeah, very, very powerful feature, I would say. And the last killer feature that I have in my mind is auto scaling. Before that, I mentioned this control parallelism, and you can specify the number of components in advance. But with this detailed monitoring, we can actually implement an auto scaling when your pipeline kind of gather statistic about how each component works, and notice that, for example, one component on average takes more time than other components, and just dynamically create another copy of this component to scale the program a bit. So yeah, that's upcoming feature, and I think that's it. Thank you guys. Now I'm ready to stop the presentation and answer your questions, or at least exit full screen mode.
So you showed the benefits of flow-based programming. What are the costs or the cons? Where would I not want to use flow-based programming?
It's a great question. So definitely you don't need flow-based programming if you write a simple logic. Yes, so if you're just sorting lists, no need to use flow-based programming for sorting lists. It's more like framework for big application when you really need to separate these layers and to present like your high-level logic, high-level complicated logic in a different way. In terms of performance, actually, it costs almost nothing. I prepared also links. Can you see my screen still? Yeah, I also prepared links for curious people, and you can see here flow-based REST API with Flowix and Plug article that was written, I don't know, a long time ago. But in this article, I actually there is a section about performance of these stages, and I kind of compared how many requests per second this pipeline can get compared with like synchronous evaluation of the same code. And of course, if you just do a synthetic test when your component just almost do nothing, of course, this GenStage works much slower. But if you just put like process sleep 10 milliseconds into one component, or like calculate some factorial in other component just to simulate a bit input output waiting time, or like some process intensive tasks, there is almost no difference. So GenStages and GenServers are really great abstractions. So all these communication or infrastructure level overhead is really, really slow. So from performance point of view, I cannot see any obstacles to use GenStages for that.
Thank you.
Hi, hi, this Wei. It's a wonderful talk. Just have a few questions. Say you have something called manager, and then you have pipelines, right? So does the manager hold any states, or is like does it hold any state of the pipelines, or what's the main function or responsibility of the manager, or is it just a trigger point to trigger different pipelines?
Yeah, thank you for the question. So actually, currently, pipeline manager do lots of things, and I'm even thinking that maybe I will split this responsibility into several components. Because currently, pipeline manager, of course, has state. So basically, pipeline manager, when you start your pipeline, Wait, could you please mute yourself for a moment? So when you build the pipeline manager kind of has all the structure, all these components. So pipeline manager knows about each component and know how to start them, even how to restart them. If pipeline crashed, pipeline manager kind of restart this pipeline. And also all the logic of streaming inside the pipeline manager. And there are, again, quite a lot of state because pipeline manager controls every packet that was sent to the pipeline, specifies specific pipeline manager gives specific ID reference to each packet to control what is returned. There is the so-called stream registry when pipeline manager kind of control which packet was processed, which is not. And for example, when pipeline is crashed, it tries to resend these packets. So there are lots of states and lots of responsibility in pipeline manager. So it's kind of the main working, not a working, but the main coordination point of the whole framework. But this pipeline manager is again it's run each pipeline has its own pipeline manager. So if your program consists of many pipelines, you kind of run many pipeline managers.
Cool. In your slides, there's a count when you say when you want to speed up the process that you can spin up a lot of sort of subscriber to the upstream pipeline. So is that in order, or it is like, or you don't care about the order because if you have spin up 10 downstream pipelines, you don't actually want to get the result in order or not?
Yeah, so basically, yeah, again, a very good question. Yeah, currently, this streaming interface, you are not sure that your events will be in the same order that you send to pipeline. But also, ALF currently allows you to send events with predefined reference or predefined ID. When you send a tuple, when the first element of the tuple is your ID of packet, and the second tuple and the second element of the tuple is your actual event. And when event is processed, you also will get a tuple with a reference and process data. So you can, if you really need these, if you really need to be sure that the data process in some order, you can control it on your side. So you can predefine reference to each packet, and then when you got the result, you can kind of make decision what to do based on these references.
Cool. I think my last question is about the auto scaling you mentioned. So say your whole application, I would assume that it starts with just one node, right? So when you're talking about auto scaling, I'm assuming that it is not only referencing to spinning up more processes. I'm thinking, will you consider the scenario that say in the cloud native environment, you probably spin up a lot of pods to scale in the pod in replica. So I'm not sure how you're going to structure, say, when you spin up a lot of nodes in terms of like VMs or pods in Kubernetes. How do you plan to communicate with each other? I'm just assuming maybe you want to spin up just one pipeline manager, and then the rest of the pipeline pods we connect to talk to the pipeline manager, something like that. I'm not sure. Is any plan for that, or how going to implement this scaling in terms of like multiple nodes?
Yeah, that's a great question. So actually, auto-scaling that I'm talking currently is about scaling on the same virtual machines, just to put more processes, more GenStages that will be related on the same virtual machine that uses the same like 10 or whatever cores that are in the system. So in that sense, this auto-scaling has a limit, because if you have a slow virtual machine with one core, so this auto-scaling doesn't help a lot. So, and your question is about how to implement the scaling when we have a cluster of machines. But actually, I don't have an answer. So I kind of hope that it's possible in Elixir Erlang to, at least it's possible to create processes in a different virtual machine, but frankly, I don't know how it implement. Is it okay with GenStages to run stages on a different machines? I would say that at least your pipeline, one pipeline should be at least in one machine, because if you have a cluster, sending messages between machines in the cluster is quite expensive. So I would say if you wanna like infinite scaling, you should run a separate pipeline on a separate machines, and then coordinate the work on a higher level on like kind of in your code, not in ALF itself. That would be my answer.
Cool, thank you very much.
Any further questions for Anton? Probably got time for one more.
I have a quick one. I don't know if the question's quick. I don't know if the answer's quick. What is the performance impact? I may have missed a slide if you covered it already.
Yeah, that what I mentioned. Let's quickly check. Yeah, you can see my screen. Yeah, I go to this link. Check these numbers. So basically, yeah, 4 years ago, it's quite a simple application just to kind of not process data, but create something meaningful. So you will see the pipeline that just it's a web application that fetch parameters, authenticate client, find record, prepare data, and the response. Yeah, but all these functions are pretty simple. You can see defined here, the render data users, find user, just repo find, etc. And then initialization, branching, and benchmarks. And yeah, and there is like how many requests in pipeline and how many requests this code produces using synchronous evaluation. And you see that the difference like quite significant, yeah? But this is because the example is very artificial one. And then for the next benchmark, I added timer sleep to find record pipe in order to simulate 1 millisecond database delay. Also I think that will calculate some factorial to render response component just to simulate processor intensive task. And component and this factorial calculates also take 1 millisecond on my machine. So it's kind of
okay.
small load.
So
and you
it's
can
basically
see that, there's
extremely quickly overwhelmed by any kind of slow process that's blocking. Okay, cool. Thank you.
No. I want to say an opposite, that you can see that if you kind of implement real-time example, that there is no difference. So basically, the coding pipeline is related the same synchronously. And even you add, and if you add more, even 10 milliseconds, you see that there is no difference. So there is, of course, some performance like so there is some processing on a low level in GenStage of sending these messages between all these processes, blah blah, but this overhead is extremely small actually. So Erlang is very cool tool.
Awesome, thank you.